Yeah, we just demonstrated interrupts where I was looking at my now site, looking at what I really want to talk about now, and then the questions kept popping up, thanks to Maris. So I basically stop what I'm doing and then I answer some things. But just because these things were referring to videos and other stuff, I just simply responded to it because I know people may have the question for the whole class. Then I come back to what I'm doing. So basically, I gave a pause. I did what I had to do, and I've come back to actually continue what I'm doing. If you remember last week when we had a look at SRAM, we went through similar things with the functions, and not just the functions, with actually in the stack, what goes on into the stack. We had a look at those kind of things. So the whole idea of interrupts is that you've got your program counter. So you've got your PC always pointing to the next instruction to be executed. So let's say, not very good. Let's get rid of that. Let's say memory location 64, 64 in hex. It's 0x anyway, but so let's say it's pointing to memory location 64, and at that point you've got maybe the value of R1 to be equal to 1, R2 to be equal to 2 or something. So you've got different values in the general purpose registers, right? So the next address, which is maybe 64. So at address 64, we expect maybe load. So load R1 to R2. So load R1 to R2. So source destination. Then we say, okay, so that's the plan. But when we got to this point, is maybe a function called subroutine 1. So subroutine 1, we get it, right? So when we get to address 63, it calls a subroutine and assign it to a variable there. When it gets to this point, the program counter is already pointing to 64 as the next line, but this is the wrong instruction to be executed. Maybe subroutine 1 needs to get loaded into the stack. So normally there is a register called the link register. It will push this 64 onto that link register and make room for the new address. So let's say in this case, if it went into, let's say, address 84F, for example. So it will push the address of the stack pointer onto the program counter. So we push the address of the stack pointer, and the stack pointer will point to this address, and you'll go into the subroutine to execute it. And then when it finishes, it goes to the next one, and then the stack pointer will increase, goes to the next one, goes to the next one, until that subroutine is finished. You saw this in action last week. So we actually started working on things like interrupts. Now, there are different ways that these are subroutines. Interrupts work in a similar manner. And of course, when it finishes, it will free this memory, and then it will also get rid of the stack pointer and then push back the 64 to a program counter, because at that point we have the value of the subroutine and it can go to the next line to execute it. So we've seen this in action. We've looked at some variables. We've seen what happens in the memory. Now with interrupts, as far as the processor is concerned, so you have your processor, you can make use of the internal timers to generate an interrupt, or basically to stop the processor from working its normal execution. The 18MEGA32AP has 3 sets of timer registers that you can use, or you can use external events such as push buttons, right? So you can have push buttons as external events, or basically switches as external events, or sensors, right? You can have different sensors that you want AC signal coming, analog signal coming in. So basically you can monitor a particular pin and then use the state of the pin to generate an interrupt. That's the whole idea. And in previous classes, I gave you examples of when you need interrupt or when you need to use interrupt. So back to what we believe hopefully will be our very last class. A higher priority task comes in and then you interrupt to work. So it's just similar to a receptionist and at a hotel or some a shop or whatever. Somebody comes, press the bell, ding dong. He comes, how can I help you? That's an interrupt. The mother is talking to the receptionist, then the child drops something, the mother stops the communication and attends to the child because she's also interrupts. So you can have interrupts in hierarchies like that. So because she is interrupt, she needs to stop, attend to the child, and then when she finishes, then she comes back to attend to the processor. So in this particular reception is called processor in this case. Now we're looking at how we can generate external interrupts. So there are a few. I've taken these extracts from the data sheet, which you already have access to because we mentioned the data sheet is really big. So today I'm using slightly different approach for my presentations because I'm talking you through this, right? So we are interested in external interrupts because that's what you're using for your assignments, like external switch, or that's what I expect you to use for your assignment. And we talk about the fact that we've got different types of Arduino boards, but we are interested in the Arduino Uno R3, which has the 80MB32 chip. So for the Mega, for example, you've got 5 interrupts, and I did show you a picture of the Arduino Mega because by now I expect you to know that you have alternative options. So you've got 5 interrupts that you can use, and these are the pins that the interrupts are connected to. So on the Arduino Uno R3, you've got your two pins that you can use as interrupts. So the other application that I said use a lot of input pins, you can use 2 of them as interrupts. So you've got interrupt, you've got pin 2 and then pin 3 that can act as interrupts. So if we look on the board, you notice you've got 0 as your receive and 1 as transmit, where the receive and the transmit is used for the serial communication, or basically if you have Wi-Fi. So basically they're just used for communication in general. And then pin 2. So if you remember, this is port D0, port D1, port D2. So PD2 is actually connected to interrupt 0 and PD1 is interrupt 1. Now, when you are creating your circuit, if you understand this, you will know which one to connect your input switch to. Okay, I'll leave it there, right? Okay, so we've gone through the board several times. We know the layout, we know how it works. If you want, we can just have a look at it again, but we don't necessarily need it. But this is just a wrap up so you know which pins are which. Now, I need you to note something, especially those who are saying how to use registers for port C, blah, blah, blah. It's the same as port D. The only thing is, under normal circumstance, if you're using the 80MB2HP chip directly, you wouldn't connect PC6, which is pin 1. So if you have the chip where the notch is, not sure whether you can see, but you can see the notch here, you can see the notch there. So this make that pin 1, right? So where the notch is on the left hand side of it, that's pin 1, is the reset pin, because if you connect it, you most likely reset the Arduino. So it's only when you want to bypass the Arduino IDE bootloader and then you want to upload your code directly to the chip, that's when sometimes you make use of that pin connection. So a closer look at the pins for the 80MB32 We've got the 3 ports which we are familiar with, and we know this digital, this analog, this also partly digital, and on there you've got the pin LED pin as well. We've shown the circuit diagram and everything as well. So port D actually ranges from the actual 80MB32 AP chip, pin 14 to 19, and then 9 and 10. So if you look on here, pin 14 is PB0 all the way to 19, that's PB5, and then pin 9, 10, PB6, PB7. So that's the actual pins that you have on there. Same port C. So port C, you've got 23 to 28, and then pin 1. So we've already seen pin 1 being PB6, which is the reset pin. So under normal circumstances, you wouldn't use this. And then also you've got the other ones, which was 23 to 28. So we've got PC0 all the way to PC5. And of course, the remainder, you've got your ground and your voltage and ground, and then you've got your analog reference voltage, and then you've got port D from pin 2 all the way to pin 6, and you jump to pin 11 all the way to 13. It looks all over the place, but this is how the manufacturers decided to create their chip, so the packaging of the chip. So that's how it looks like. So the key things, some key things: avoid pin 1, obviously is the reset pin, and then also the analog pins are connected to ADC025. Please, at this point, I expect you to be transferring the knowledge you have acquired. If you can work on port D, you should be able to work on port C. You just have to understand it rather than memorize it. Okay, good. So we've mentioned the serial pins, and also we've mentioned the interrupt pins as well. Now we are familiar with these 3 ports, which controls the port that we are using. So we know the port, we know data direction register, and then we know the pin. So we know there are 3 of them, and the port obviously tells whether it's pull up or whether it's a voltage or those kind of things. We've been through that, right? Okay, so the same thing comes here, highlighting the reset pin, because you can't think of it as even more important as it is now, because it is important, right? It's the pin ordering of the chip now. So basically we're stepping more into architecture. Now we have the CPU on there, and then we've got the data IO registers, the 3 IO registers that we are considering. And remember, for the port, if it is configured, if this is configured as an input, so basically if you connect this to that using the data direction register to set the direction of the port, if it is connected as an input and you write a 1 to it, you are basically connecting this 0 connects it to the ground, and the 1 will connect it to the 5 volt or the pull-up resistor. The pin brings the value, and we wouldn't want to repeat everything. So basically, if you are looking for a recap of the whole thing, this is your recap, right? We are familiar with this. We know where it's coming from. We know it's coming from the Arduino reference. We've broken it down. We've understood it. And this is basically what you see in your assignment brief as the example, but we've been through the register manipulation. That takes us to the interrupts. So just as the port, in order to get a port to work, we needed 3 registers. In order to make the external interrupt to work, we need different registers to work with. I'll stop.